Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem partition array for maximum sum. We're given an integer array. It's guaranteed that all values in this array are going to be greater than or equal to 0. And we want to split this array into subarrays. So consider the array over here. The only restriction that we have is that when we split it into subarrays, any given subarray is going to have a length of at most k. K is going to be a second input provided to us. It's guaranteed to be positive. It's going to be at least greater than or equal to 1. Now, what we're trying to do when we split this into subarrays is somehow maximize the largest sum. When we take this, suppose we were to take this and split it into something like this, 3 elements over here, and then the other 2 elements are over here. The reason for doing that, suppose this subarray originally looked like this, 1, 2, 3. Those were the values over here. And suppose this looked like 4, 5. What we do is actually replace every element in this array with the maximum element. 3 is the maximum element, so what we actually get is a subarray that looks like this, all 3s. Same thing over here, the maximum is 5, so we end up with a subarray that looks like this. And then from this, we take the total, and that is considered our sum now. So this is 9 plus 10, we ended up with 15. What I immediately noticed, or at least what I asked myself, is what do the extremes look like? Because one possibility for us is to actually take the input and just split it into subarrays of size 1. That's perfectly allowed. It doesn't matter what our k value happens to be. It's going to be at least greater than or equal to 1. So we're perfectly allowed to do that. But notice how that's actually not going to increase the sum at all. Our original array is going to stay the exact same because every subarray's maximum element is the exact same. The other extreme would be, what if we just took the entire array as the subarray? Well, then we would just take the maximum from the input array, and then every value would get that maximum. This is the other extreme where we have pretty much maximized the sum of the subarray. The previous one was where we didn't change the sum at all, and in this case, we pretty much made it as large as it could possibly be. But the only downside of this approach is we might not be allowed to do that. K might not be the size of the input. So at this point, you might kind of try to get greedy. You might try to make the largest subarray that you possibly can every single time, but you can kind of tell even just from this example, that's not going to work, because let's say in this example, k was equal to 3. The solution would be to split it into a subarray like this and this, because this chunk would end up being 4. We get 3 5s over here. That's going to be 15. Okay, so I guess in this case, it actually was the same as doing it this way. To make it more extreme, what if I just changed this to a 6? Then this would have ended up being 12. This would have ended up being 9. That's going to give us 21. But if we were to have done it the other way, where we get 3 6s over here, that's 18. Then 4 is over here, we get 22. Basically, I'm saying there's not really a clever way of doing this greedily. I don't know if that's a word. So now let's kind of go back to the drawing board. Let's consider maybe a brute force approach and see if that can help us out. To even consider the brute force, let's first pick the first subarray that we could possibly choose, because we know we have at least 3 choices when our k value is equal to 3. Let's say k is 3 for this example. For the first subarray, we either get this, or we get this, or we get this. So basically we can say, starting our pointer at I, we're going to have a for loop that goes up until I plus k minus 1, basically like the boundary. For each of those possible subarrays, we know we're going to have additional choices. Let's say this is our first subarray. Well, for the next subarray, we could have either this, or this, or this. So this problem lends itself to recursion, at least trying to brute force it this way, because what we can say is I initially starts at 0, and we can make our I pointer go to 1, we can make our I pointer go to 2, or we can make our I pointer now start at 3. This I pointer determines the start of the subarray. So we know initially we start at 0, index 0. For the next subarray, we can start at index 1 or 2 or 3, depending on what the previous subarray looked like. And once we shift that I pointer, suppose it's over here, now this is basically a subproblem. Now we're asking, starting from here, how do we do it? Eventually, our I pointer will go out of bounds. That's the point where we would return 0. And if you want to be clever and you don't want to ever have to even return 0, suppose our I pointer is here. We know normally we'd want to iterate up until this many times, we'd want to consider this subarray, and this subarray. But we recognize that the length, the last index of the array, is smaller than I plus k in this case. So in the code, I'll be basically taking like a minimum of the length of the array and I plus k. And whichever one of these is smaller is going to be our boundary. So in this case, the length is going to be smaller, so that's what will be our boundary. Okay, but for the actual computation, we have the base case down, we have the recursive steps kind of down, but how do we actually accumulate the result? Let's consider this case again. Let's say this was our subarray. Let's say this is where the subproblem is going to be. This is going to be the recursive call. Well, it's not I plus 1, it's just I. To make it even more clear, we're going to use 2 pointers actually. Let's say I is going to be the pointer for the beginning of the subarray, and j is going to be the pointer for the end of the subarray. And then the recursive call will be called, let's say, with j plus 1. So simple enough. Now, as we are building this subarray, as we are considering each possibility, this one and this one and this one, we can maintain something called the current max. By the time we're here, our current max is just equal to 1. By the time we get here, our current max is 2. By the time our j pointer gets here, our current max is 3. With that current max, we can say so far we have accumulated 3 times the size of the window. And getting the size of the window, as long as we have these 2 pointers, I and j, is not going to be difficult. It's just going to be j minus I plus 1. You can check my math on that. If you don't believe me, try it out with a couple numbers as examples. That's the idea for solving this problem with recursion. We talked about the base case, we talked about the recursive step, and we talked about how we're going to take the recursive subproblem result and add it with this, because we can take our current max and multiply it by the window size. That will give us whatever is in this section. So this solution is definitely a brute force solution. We're going to see that this becomes exponential. The size of this tree is going to be k to the power of n, where n is going to be the height of the tree because I is going to basically determine the height. K determines how many branches we have at each level. We can optimize this. We will see the same subproblem many times from here. We're going to see this subproblem I equals 2. We're going to see the subproblem I equals 3. We know we've seen that subproblem here and here. So what we can do is add a technique called caching or memoization. So this is basically a dynamic programming technique. And using that, we can get the number of subproblems is going to be n. Obviously, I is what determines a subproblem. But to solve each subproblem, we have to iterate k times. So the overall time complexity is n, the number of subproblems, multiplied by k, how much it takes to solve each subproblem. And that's the overall time complexity. And the overall memory complexity with caching is going to be big O of n. That's how many subproblems we're going to save the result of. Now let's code it up. So I'm going to first declare our recursive function. I just like to call it DFS because it's recursive, and we kind of go along each branch. And we only keep track of one parameter, our I pointer. Usually I would just add the base case, like if I is greater than or equal to the length of the array, just return 0. And I guess I'll leave that there for now. But the way I'm going to code this up, you'll find that this actually becomes redundant. Next, we're going to declare a couple things. One is the current max element we have so far, like within our window. And second is going to be the result of this subproblem, which we're ultimately going to return from here. Now let's actually build that window. We have our I pointer. It tells us the beginning of the window. Let's have a second pointer j for the end of the window. And it's going to go from I up until I plus k. Normally, this would be the case. It's possible I plus k goes out of bounds. If you don't want to have to deal with that edge case, what we can say is just take the minimum of length of the array and I plus k. And remember that in Python, these are non-inclusive. The second endpoint of the range function is non-inclusive. The length of the array is technically out of bounds. I plus k is technically further than we would need. We actually would want I plus k minus 1. That would be what j is for the largest window. So that's why it works, because these are non-inclusive. Like I said, the main thing we want to do is just keep track of what's the maximum we have seen so far. That's easy enough. Take the maximum of the current max as well as the current element that we're at pointer j. Let's also determine the window size, which is pretty easy to do. Let's get j minus I plus 1. Now we're ready for the recursive call. The recursive call is pretty simple. We know that our right endpoint is j, so the subproblem is now going to be j plus 1. But with that, we want to add the values that we're getting from the current window. We can get that by taking the current maximum and multiplying it by the window size. And by taking that and adding it with this, we get the current result. But we know we want to maximize the result. So what we can do is take result and set it to the max of itself, as well as what we just computed right here. This is kind of the brute force solution. You could call DFS out here starting at the beginning of the array and then return that. But without caching, this is going to get you time limit exceeded because it's very, very inefficient, but it's pretty easy to improve the efficiency with caching. I like to declare a hash map. It's usually easier. And now I'm going to add a base case for that. If I is already in the cache, we can return the result that we ended up computing. We don't have to do the extra work again. We don't have to iterate again. But if it's not, then before we end up returning, let's make sure we add the result into the cache. So just like this, cache of I is equal to the result. So this will pass. I want to quickly mention why this code here is redundant. Will we ever call DFS with a value greater than the length of the array? If you look at our J pointer here, actually, we will. Like, look, j might end up being the last index in the input array. And in that case, we would probably end up calling DFS on j plus 1, which would technically be out of bounds. So then what would happen? Let's say I remove this piece of code. What would happen if j plus 1 is technically out of bounds? What if I is out of bounds? What's going to happen here? Well, I, starting at this number, we're going to go up until this number, which is invalid. This has to be smaller than this part. So what's going to happen is this loop isn't going to execute anyway. The result is 0, and that's what we're going to end up returning. So that's why that if statement before was redundant. But again, that's not really a huge point. So if you leave it there, it doesn't really cost you anything. But I'll go ahead and run this code now. As you can see on the left, it's efficient. But let's try to solve this problem with tabulation without recursion. So when trying to go from memoization to the dynamic programming solution, the main thing you want to start is like the dimensions of the solution space. We know it's one dimensional because that is the dimension of our cache, and it's going to be kind of the same length as the input. The way we kind of did it with recursion was if our I pointer ended here, this would tell us what the result of the subproblem would be. Basically, what's the max sum if we were starting from this part of the array. And then recursively, we started from here, but then we went top down. Now we're going to kind of go bottom up. So if you wanted to, you could iterate in reverse order, solve this subproblem, solve this. And then if you wanted to solve this subproblem and you already had all these values filled in, it would be easy because you would consider the 3 possibilities because k is equal to 3. You'd consider this possibility, basically the sum of this array, and then the subproblem would be here and you'd add those two together. The other possibility is this subarray. Get the sum of this subarray and then consider the subproblem, which result is stored here. Lastly, this subarray, get the sum of that, and the result of the subproblem is stored there. The only thing is, to do that, you'd have to iterate in reverse order. I used to implement my DP solutions like that, but for some reason, people prefer just going from left to right, even if it kind of changes the math formula from memoization to DP. So I will go from left to right, which means this is kind of our base case. And if we were to solve the problem from here, we would consider this subarray, and then the result of the subproblem would be here. We'd consider the subarray of size 2. The result of the subproblem would be here. We'd consider the result of the subarray from here. The subproblem would be stored here. That's what I'll be doing. The base case is pretty straightforward because we can just take that one element and move it there. So that's what I'm going to do, put 1 here. To fill in the value here, we're going to go consider this window. In terms of pointers, I'm going to, in this case, have our I pointer basically tell us the end of the window. And now I'm also going to have a second pointer j tell us kind of the beginning of the window. So first, j is going to be here. We have this window. The value itself is 2. The size of the window is 1. Our max element so far is 2. So to get the sum of the window here, we do 2 times 1. Simple enough. And then the result of the subproblem would be dp. We know the end of our window is at index j. So to now get the value over here, the subproblem, which is I'm calling it, I'm going to take dp of j minus 1. Next, we would consider the larger window of size 2 because it's technically valid. Our max element is still 2. We'd compare it with this. So now our sum here is 2 times 2, which is the size of the window. We get 4. And by the way, this time j would have been shifted over here. And now to get the result of the subproblem, we can again take dp of j minus 1, but this time it's going to go out of bounds. So we can add a check here to make sure that j doesn't go out of bounds. If it goes out of bounds, we can kind of just assume that there's a 0 here, kind of like in the base case of like the recursive solution. Now we found that 4 is the maximum element that we can put over here. So that's what I'm going to do. Now we're going to have our I pointer here, and then same thing, j is going to be going from here all the way to the beginning, and that's how we're going to fill this value in. We'll initially consider just 3, just that window, and plus the result of the subproblem, which is 4, and that's going to equal 7. 7 could go here. The other case is this window, which would be 3 times 2, because that's the size of the window. We'd get 6. The result of the subproblem would be stored here. That's also 7. Third, we consider this entire window, which would be 3 times 3. That's the length of the window. So we'd end up getting a 9 here. I won't continue with the rest of this, but you probably get the idea at this point. Notice that this is actually not any more efficient than the previous solution. Over here, we're going to end up getting a 13. And I think here we're going to end up getting 22. The memory is still big O of n. The time complexity is still going to be big O of n times k. But there's something clever you can notice. Anytime we're trying to compute a value here, we're never going to look further than k previous computational values for the subproblems. We only want the previous k values stored in memory. It is technically possible to take this and actually just have 3 elements stored in memory at a time. Let me quickly show you how we can make that optimization, and that's the one I'm going to be coding up. To start with, it's going to be the same as we had before. We're going to end up populating 1 here, we're going to get 4 here, and then we're going to get a 9 here. We're trying to compute the value that would go here. And we're going to do it the same way, except now we're going to put it in a temporary variable. I'm going to call it max at I, and you'll see why we need a separate variable for this. So this is where we're going to store the result of that in because it looks like we've ran out of space. And eventually we're going to get that value 16, right? We're going to do the same thing as before, and we'll end up finding 16 is the value that goes there. Now, where do we put 16? Because now we've ran out of memory. We want the previous k values to be stored here, but we ran out of memory. One possible approach is to take this element here, remove it, and then push the element over here, the new element 16. So then we'd still have the subarray of size k. The values would still be in the order that we want them in. That would work. I think you might be able to do that with a queue, or you might just be able to manually shift all of them. And it would still be a big O of k operation, so I don't think it would change the overall time complexity. But I saw that in the editorial, they had the circular array solution, and I guess I wanted to explain that to you in case you were confused by it. There is something clever you can do by taking the index I, in our case, which sometimes can go out of bounds. How can we ensure that this is in bounds of this array? Well, we can use the mod operator. We can mod it by k. That will guarantee it maps to one of these indices. Let me just show you how it would work. 0 modded by k stays 0. It goes here. 1 modded by k stays 1. 2 modded by k stays here. 3 modded by k becomes 0. Now it's going to go there. 4 modded by k becomes 1. It's going to go there. 5 modded by k becomes 2. And it's going to kind of cycle like this. This is going to go there. 7 would go here. 8 would go there. Obviously, I ran out of space. But that's the idea. Anytime you want to map an index I that is greater than or equal to k, we can just mod it by k. It's very difficult to kind of visualize that. So I'll run through this example. So now that we've computed max at k, the reason we're putting this in a separate variable is because we don't want to overwrite any of the previous k values until we've actually computed the final value that's going to go here. We don't want to overwrite this guy with 16 before we've actually considered all 3 possibilities, which in this example, we'd have 4. 4 is that subarray. Now we want the previous value. We would take whatever that pointer is. I minus 1, mod it by k, and in this time it's in bounds, it'd be 9. So we'd say 4 plus 9 is 13. So we'd have 13 stored here right now. We'd also consider this subarray, and then we'd consider this one. We'd finalize, I think it would be 13. I don't know why I had 16 earlier, so sorry about that. So now we're here. We want to compute the problem where we're ending at this index. So we can consider this subarray by itself, 6. And to get the previous, I modded by k, and for whatever index this is, would be mapped over here. You can check the math if you don't believe me. So I minus 1 modded by k would be mapped over here. Basically, the math works out. It's not super intuitive unless you've kind of seen this before, but I promise you the math works out. So the previous is here. The result of the previous subproblem, 13 plus 6, is going to be 19. That's what we would have so far. Next, we would consider this. Subarray of this is going to be 12 plus the result of the subproblem, which now is going to be I minus 2 modded by k, which is going to bring us all the way back around to the end. The math, if you don't believe me, is going to be 4 minus 2 modded by k. K is 3, so we get 2 modded by 3, and that's going to remain 2, which is this last index. So we'd get 12 plus 9 as a possible result, which is going to be 21. So far our max would be 21 over here. And lastly, we'd consider this. The sum of this guy is going to be 6 times 3, that's 18. And we'd do I minus 3 modded by k, which is going to be 4 minus 3 modded by k, which is going to be 1. And that value is over here, 4. So we'd get 18 plus 4 is going to be 22. And that's going to be ultimately the value that we now end up storing over here. Because the index of 6 is 4, it's going to map here to index 1. And we'll overwrite this value once we've computed the final max at I with 22. The only thing is, to return the result, we will again have to do that mapping, because we know that the last value that we compute is going to be the result. We just don't know where it's going to be stored here until we've done that mapping, until we've taken the length of the array, which is where the last index is, and mod that whole thing by k. That'll map us down here. This is definitely not an easy solution, and it's not like a huge optimization. I just think this was worth showing you in case you were interested, because this type of circular array does actually come up in other problems. So now that you've seen it, you might be able to solve problems requiring this in the future. Okay, so I'm going to declare dp, and this time we only want it to be at most k. So let's multiply this by k, and let's initialize the first value like I did earlier. And let's just initialize the base case to the first value in the input array. And then let's use I as the ending of our array. So we'll start at 1 and we'll go up until the length of the array. We want to maintain a couple things. We want to maintain the current max, and we want to maintain the max at I. This is the result, and this is the value that we're going to store in dp after we've computed it. So this is what we're going to do. We're going to say I modded by k is going to equal to max at I. This is ultimately the result we're trying to compute, but we don't put it in dp until it's been finalized. Once we've gone through all of that, at the end, we can return dp of the length of the input array minus 1, the last index, and mod that by k to get the appropriate mapping. So now we've done the setup. The only thing for us to do is this inside part, actually going through and iterating. So I do it backwards because it's kind of required. To expand our window, we're going to start our J pointer at I, and we're going to actually shift it to the left. So we're going to provide 3 values to the range function. The third is going to be minus 1, because that tells us how much we want to increment or decrement our pointer. So this time we actually want to subtract from it, and we want to keep going at least k times. So we could do I minus k, but it's possible that this goes out of bounds. There are many ways to handle that. I could put max here. I could say max up until -1 and I minus k. I feel like this is less readable. That's just my opinion, and it doesn't change the time complexity. So what I'm going to do is make it slightly easier and just put an if statement. If j is less than 0, let's break out of the loop. It doesn't change the time complexity, and it makes it more readable. I think it's worth doing. As we do this, as we shift j to the left, we want to maintain what's the max element we've seen so far. So we'll take max of itself, and the current element at index j. We also want our window size as we had in the recursive solution, so I'll compute that very easily, I minus j plus 1. This time I think our I pointer is actually greater. I think last time we were doing j minus I. And now we want to get the result of the current window. So we can call that current sum. It's going to be current max multiplied by the window size. That's easy enough. But we also want the result of the subproblem. I'm going to call that the subsum. You can call it something else if you'd like. But remember, that's going to be from the left boundary of our window, which is j. J is the left boundary of our window. But we want to go before the left boundary of our window. So we want j minus 1. That's where the result of the subproblem would be stored. But that's only going to be the case if j is greater than 0. If j is equal to 0, then that would give us an out of bounds error. So then we would say, well, otherwise, just assign this to 0. There's nothing left there. So this is how we would do it if we did not have a circular array. But we know we actually do have a circular array. So we take j minus 1, and to get the mapping, we take j minus 1 and mod it by k. So I do it just like this, if j is greater than or equal to 0. Otherwise, instead of assigning it to 0, because in a circular array, let's say this is our circular array, and let's say the first value is 1, for example. I'm here, j is here, j minus 1 would be out of bounds to the left over here, but circularly, we'd want to go back to the beginning. In other words, the last element in the array. So actually, in Python, to get the last element, we can say dp at -1. It's possible we haven't even populated that element yet, in which case this would evaluate to 0. But if we have populated it, we'd want the real value stored there. So that's why I'm doing it like this. Now that we have the current sum and the subsum, we want to add them together, and we want to maximize them, and then we want to assign it to this variable up here, max at I, which is what we end up placing in dp. So max at I is equal to the max of itself, as well as the current sum plus sub sum. So this is the entire code. It's not easy to come up with, is it? I don't think the expectation for this problem is that you come up with it, but I wanted to teach you this pattern. As you can see on the left, it works, it's efficient, and this is the most memory optimal solution. If you're preparing for coding interviews, check out leetcode.io. Thanks for watching, and I'll see you soon.